Now, using the axiom of induction in the previous slides might have been a little confusing, so we're definitely going to want to focus on that. It's going to be very important for us moving on. Okay, so we've already seen one example of how to use the axiom of induction, but we're going to do a few more to get more comfortable with it. Now, the axiom, as formally stated, was, for any subset of the natural numbers, if 0 is in that set, and for any n, which is a natural number, if n is in the set, then n plus 1 is in the set, then overall your set was all natural numbers. Here I've simply replaced s of n with n plus 1 because we've already proven in the previous slides that n plus 1 and successor of n are always the same thing. So instead of an s of n here, I've replaced it with n plus 1. But this is the axiom formally. For any subset of the natural numbers, here's the hypothesis overall. If 0 is an element of the set, and for any natural number, if n is an element of the set, then n plus 1 is an element of the set, well then overall, your set was all natural numbers. So to show a set is all natural numbers, you show it has 0, and if it contains a number n, then it must contain the number n plus 1. If we can show both of those things, it contains 0, and if it contains n, then it contains n plus 1, then axiomatically we have shown the set contains all natural numbers. Okay, as mentioned, we've replaced s of n with the more intuitive n plus 1. We're almost always going to let the successor function float away and not be mentioned explicitly. In the previous example, we let a be the truth statement of a predicate. So if we can show that a statement is true for 0, and assuming it's true for n, we can derive that it is true for n plus 1, then the statement is true for all natural numbers, and that's basically what we do. That first step is called the base case. Show that for a specific number, 0, the statement is true. The second is called the inductive step. If the statement is true for some number n, then it is also true for the number n plus 1. This is just language to describe using this axiom. Showing the statement is true for 0, you simply call the base case, and then this conditional statement, if it is true for n, then it is true for n plus 1. Proving that conditional statement is called the inductive step. Okay. To prove the inductive step, you're typically going to assume the hypothesis is true, assume the statement is true for n, and use it to derive that a statement is true for n plus 1. Making that assumption is called assuming the inductive hypothesis. And this language just helps you communicate more clearly what you're doing or understand other people's work. Let's take a look at another example. We want to show that for any natural number, 0 plus n is the same thing as n. And you might be saying, wait a minute, wasn't this an axiom? Not quite. Our axiom stated that n plus 0 is always n. But we don't actually know that addition is commutative. In other words, n plus 0 and 0 plus n might be different things. So I can't just say, since I know adding on the right does something, that adding on the left does the same. We don't know that yet. So our claim formally is that for any natural number, 0 plus n equals n. The base case is what happens when n is 0? Well, we do have this axiom that adding on the right does not change the value. N plus 0 is always n. If that's true for every n, it's specifically true for 0. If I let n equal 0 in the axiom, I get 0 plus 0 equals 0. But that's exactly what I'd get here if I let n equal 0. 0 plus 0 equals 0. In other words, if both numbers are 0, it doesn't really matter which one you put on the right versus the left because they're both the same. So if I specifically want to show that 0 plus n equals n, on the assumption that n is 0, I would just be trying to show that 0 plus 0 equals 0, but that's just this axiom as well, with n equals 0. So the base case is established essentially for us by axiom. So we need to proceed to the inductive step. So we get to assume that the claim is true for some number. 0 plus n really is n. We don't get to assume what number that is. It's just some natural number. Now what we need to show is that 0 plus the successor of n, aka 0 plus n plus 1, is the successor of n. N plus 1. If the claim was true for n, then it is true for n plus 1. 0 plus n really is n. Hopefully we can prove that 0 plus n plus 1 really is n plus 1. And remember, forget what you know about addition. Okay, a lot of people at this point in this course would be like, but we know how to add 0. Sure, based on how you know how to add things, which is a totally different function. We're defining something radically new, it just happens to behave very similarly. Okay, so we need to show that if I get to assume 0 plus n is n, hopefully we can show 0 plus n plus 1 is n plus 1. Now the 11th axiom was stated in terms of successors. Okay, the 11th axiom originally said that the successor of a plus b is equal to a plus the successor of b. But remember, we're letting plus 1 stand in for successor because we've proved that's always what it does. So the equivalent version of this axiom is that the successor of a plus b is in fact equal to a plus the successor of b. So this is this axiom rewritten by replacing successor with adding 1. S of a plus b is a plus b plus 1. A plus s of b is a plus b plus 1. Just reverse right versus left, and we have a plus the successor of n is a plus n, its successor. So we're just taking this interpretation of that axiom and putting it here, where a is 0 and b is n. A 0 plus n plus 1, b plus 1, so that's here, is equal to a plus b, 0 plus n, plus 1. And again, that's just this axiom reframed with our existing knowledge that the successor of a number is always that number plus 1. So here's our 11th axiom. Now we've already assumed that 0 plus n is n. So altogether, 0 plus n plus 1 is the same as 0 plus n plus 1. That's this line right here. We get to assume that 0 plus n is the same thing as n. And now we're just going to do some playing around with parentheses. We just have n plus 1 here. So overall, 0 plus n plus 1 really is the same thing as n plus 1. So having assumed that our statement was true for n, we were able to prove that it is true for n plus 1. Altogether, our claim is true for 0, and if we assume it's true for n, we can prove it's true for n plus 1. So the axiom of induction now kicks in, and we would say, inductively, we have proved that our claim is true for all natural numbers. For any natural number, adding 0 on the left also doesn't do anything. And I just want to repeat, a lot of people are like, we already knew that. We axiomatically defined adding 0 on the right changes nothing. Then, using other axioms, we are now able to prove adding on the left a 0 also does nothing. And this is a nice exercise in declaring as little as possible to be an axiom. How would you know adding on the left doesn't change the value if you add 0 on the left? And a lot of people just sort of shrug and say, duh, we already know that. But why? How do you know that addition works that way? What we've established is that if addition satisfies a few basic Peano axioms, then this automatically happens. And we only had to assume, axiomatically, that adding 0 on the right doesn't change anything, and now we've established adding 0 on the left also doesn't change anything. Another example, so we're going to do another proof by induction of this statement right here. For all natural numbers, 1 times n is the same thing as n. And resist the urge to roll your eyes and say, duh. So we're going to prove this by establishing it's true for 0, and then if it's true for n, it must be true for n plus 1. So our base case is what happens if I replace n with 0? What we'd be trying to prove is that 1 times 0 equals 0. But axiom 10 told us that any number times 0 is 0. So specifically, yes, 1 times 0 is 0. That's axiom 10. So our claim is true if n is 0. 1 times 0 really is equal to 0, and that was an axiom. Anything times 0 is equal to 0. Now we get to assume our inductive hypothesis. 1 times n is n for some natural number, although we do not specify which one. What we want to show is that the claim holds true for the next natural number. If I assume 1 times n is n, can I also show that 1 times n plus 1 is n plus 1? Now the 12th axiom had to do with how multiplication and addition interact with one another, except it was originally phrased in terms of successors. This was a times the successor of n is a times n plus a. And all this does is replace successor of n with n plus 1 because, as I've mentioned, we're generally going to not use the successor notation. So for the particular choice of a equals 1, we would get 1 times n plus 1 equals 1 times n plus 1. But what did we assume inductively? What was our inductive hypothesis? That 1 times n is equal to n. We assumed that back up here. So this 1 times n can be replaced with just n, giving us exactly what we wanted. 1 times n plus 1 is n plus 1. If we get to assume that our claim is true for n, then it must be true that it's also true for n plus 1. So our claim is true for 0, and if it's ever true for some number, it's true for the next one. Altogether, that completes the inductive proof that this claim is true for every natural number. For every natural number, 1 times n equals n. And again, what we're doing is constructing formal proofs based off the axioms of stuff we pretty much already knew. But if you were ever, 6 years old and asked, why is it that 1 times 5 is 5 and 1 times 8 is 8, you may have not been given a really solid answer. Well, it sort of depends on what numbers are and what times means. And there are different interpretations, and we're going with the Peano axioms, okay? So if we construct the natural numbers and their operations through these axioms, we have now proven that it must work like this. Note, we are not claiming this has anything to do with counting beans or anything like that. We're not trying to make any relationship between this construction of the numbers and anything, I'm doing big air quotes, but you can't see it, real, okay? We're not getting into that morass. Rather, we're just saying, if we define these things axiomatically, here's some stuff we can prove about it. Well then, let's do another example of using the inductive axiom to construct a proof. We want to prove that addition is associative. In other words, for any 3 natural numbers a, b, and c, a plus b first added together and then add c is the same thing you'd get as if you had first added b plus c on the right and then added a on the left of that. The way we're going to do this proof, and there are a few ways to do it, okay, but the way we're going to do it, pretend a and b are arbitrary but not changing natural numbers. The claim is then going to be, for any choice of c, this works out. So we're going to do an inductive proof where this variable c is the one that we are letting vary across all the natural numbers. So for a base case, we need to show that it works out when c is 0. Well, adding on the right doesn't change anything, adding 0 on the right. So whatever a plus b is, a plus b plus 0 must be the same thing as a plus b. But also, b plus 0 is the same thing as b. Again, this is just adding a 0 on the right of b. So overall, this here is a plus b, but so is this. So these two things must be equal because equality is transitive. So a plus b plus 0 really is the same thing as a plus b plus 0. In other words, our claim is true, specifically when c is 0. Now we go to the inductive half. Assume that for some choice of n, these two things really are equal. Now we need to prove that it's true when I replace n with its successor. And I'm actually going to go back to using successor notation here. If I used n plus 1, there'd be a lot of parentheses and a lot of plus signs floating around. I think in this case, using the successor rather than n plus 1 is a little cleaner notationally. So we're going to use axiom 11 over and over again. Axiom 11, recall, was the one that said the successor of a plus b is a plus the successor of b. We're going to do that a bunch. Some notation and sort of markup is going to be handy for us. Okay, specifically, I'm going to let b plus n, it's a natural number, and I'm going to call it the red box number. So here I have the red box number, and here I have the red box number, but that's the only place I have it on this line. So the first thing we do is inside this parentheses, we say b plus s of n is s of b plus n. That's axiom 11. Now let's think about that a. A plus s of red box is s of a plus red box. Just because this happens to have a plus sign in it does not change the fact that it's just a number. So first, in this parenthesis, b plus s of n is s of b plus n. Now incorporating this whole thing, a plus s of red box is s of a plus red box. Conversely, we can do something else. If I call a plus b the red squiggle number, then here I have the red squiggle and here I have the red squiggle. So we can say squiggle plus s of n is s of squiggle plus n. But our inductive hypothesis was that a plus b plus n is a plus b plus n. In other words, our inductive hypothesis is that squiggle plus n is the same number as a plus box. Okay, the box was b plus n and the squiggle was a plus b. So now I can chain all of these two things together. A plus b plus s of n is s of a plus box. But since a plus box is squiggle plus n, s of a plus box is the same thing as s of squiggle plus n, and now I get back here. So overall, a plus b plus s of n must be the same as a plus b plus s of n, which is exactly what we were trying to prove up here. Having assumed the statement was true for n, we derived that the statement is indeed true for s of n. That completes the inductive proof. The base case, it does work out if c is 0. If I replace c with n and assume it's true, I can then derive that the statement is true for s of n. That's the inductive part. Overall, we have now shown that whatever a and b are, for any choice of c, all of this works out. And now we know that addition is associative, something that we knew, sort of, but now we've proved it. Where do we go from here? So the point of all of this is that the rules of arithmetic we already know are actually true and can be proved, and they can be proved with as few axioms as possible. We don't want to introduce extra axioms because we may accidentally contradict something. Also, if something can be proved from axioms we already have, then it wouldn't be proper to introduce it as an axiom. An axiom specifically is something that cannot be proved, that is logically independent from what we already have floating around. So what's been worked out is that the Peano axioms are all independent from one another, and using them we can prove everything else we know about arithmetic. Okay, so we can't actually prove one axiom using the others. If you think about, axiom 9, a plus 0 is equal to a, that seems obviously true. But trust me, you can't prove that using the other axioms. These axioms are now a framework from which all familiar properties of arithmetic can be proven. We have proven, for example, the associative property. A plus b plus c is the same thing as a plus b plus c. We're not, however, going to go through and laboriously prove every single one of them. Addition is associative, addition is commutative. Multiplication is associative, multiplication is commutative. You have a distributive property for multiplication with addition, whether you multiply on the left or on the right, blah, blah, blah. Okay, it takes forever. We're not going to go through every single one, but it is good exercise to do one or two of them on your own. Okay, but from this point forward, we're just going to assume that all the familiar rules of arithmetic have been proven so we can use them freely. Now, if you do like this sort of derivation of basic arithmetic using the axioms, try to show things like a times b times c is the same thing as a times b times c. That a plus b is equal to b plus a, and so is a times b equal to b times a, associative and commutative properties of both multiplication and addition. Distributive properties like this. All of these things can be inductively proved, and it takes time, but it's a good exercise. Okay, also a handy one to know is that you can cancel out. If a times c is equal to b times c, then a must equal b, provided c was not 0. Notice there's no such thing as division. Since we're only working in the natural numbers, we have multiplication and we have addition, but we don't have subtraction and we don't have division. Those things don't exist yet. So you can't just divide both sides by c because there's no such thing. Proving this is not a matter of dividing both sides by c because division has not been defined. This has to be proved inductively. Okay, and it's a nice little exercise.